Right. Welcome everyone to the series of UKAN Physical Acoustics webinars. Today we are delighted to have Robbie Balcom from COMSOL presenting numerical simulations of the range of acoustical problems related to building acoustics, but not restricted by building acoustics. Dr. Robbie Balcom did his MNG in Strathclyde University and continued with PhD at Imperial doing numerical modeling, and then I should say now working with COMSOL as a technical director. So the webinar has a Q&A session, and everyone's welcome to ask the question on the chat. So it will be tracked by COMSOL, and so there will be some immediate answers. All these will be answered later in the question time. I should also remind everyone that the webinar will be recorded and then later uploaded on the UKAN Plus YouTube channel. And I think I will pass the floor to Robbie to maybe introduce into more details in this webinar and start this webinar. Thank you.
Perfect. Thank you for the introduction, Anton, and thank you for asking me to present and giving me the opportunity to present at this webinar. In terms of what I intend to cover during the webinar today, Anton was kind enough to share with me some topics that he felt that would be relevant for this audience. So what I've done is I've put together an agenda to try and cover a number of these relevant topics. What I would say, though, is that I'm going to try and cover quite a lot of ground during this webinar. So I will endeavor to cover as much of the content as possible. But I may not have time to cover all of these different sections in detail, but we'll see how we get on. So in terms of what I'm going to start by doing, I'm just going to go through a very, very brief introduction to COMSOL Multiphysics, just really to lay the foundations for those of you who are unfamiliar with the software. Then what I'm going to do is I'm going to move on to talking about numerical methods, and I'm going to talk about numerical methods in the context of acoustic modeling. So I'm going to discuss the different numerical methods that we can apply to solving acoustic problems. So essentially what we have is we have a set of tools that we can use to simulate acoustic problems, and we want to make sure that we're using the right tool for the job when it comes to setting up and running our simulations. I will also talk a little bit about coupling different numerical methods together. So we would typically refer to this as using a hybrid approach to running our simulation, where we might combine more than one numerical method within a single acoustic model. I'm then just going to take a short break, just a comfort break for myself and also for you in the audience. And then in the second half, what I'm going to talk about is modeling of porous materials. So some of the methods that we can use for simulating porous materials and how we can set up and incorporate these in our simulations. Then I'll talk a little bit about the distinction between time domain modeling and frequency domain modeling. And this kind of segues nicely into modeling of nonlinear effects in acoustics, something that requires us to work in the time domain. And I'll also talk a little bit about how we can set up and run simulations on nonlinear effects. I had also intended to cover a section on modeling of open and closed acoustic problems. But given my time constraints, I don't think I'm going to have time to cover this in detail. But if there is time available, I can go through this in a sort of edited version, shall we say. And as Anton mentioned, there will be a Q&A session at the end. So if you want to send in your questions during the presentation, if there's an opportunity to answer them whilst I'm presenting, then I can do so. Otherwise, we can address these questions at the end. And if we don't have time to address your questions, then perhaps we can follow up with you after the webinar. Now, I just wanted to mention that by virtue of attending this webinar, you can get, if you are interested in learning more about COMSOL and evaluating the software, you can get access to a trial, and you can contact my colleague, Oliver, if you would like to be provided with a trial after the webinar. And this would be a 14-day trial that will include access to COMSOL support. I will give you these details again at the end of the webinar, again, if you're interested. Okay, so first of all, really just to go through a sort of introduction to COMSOL Multiphysics. So COMSOL Multiphysics is a commercial modeling software that's based around a graphical user interface, and it will allow you to simulate physics and engineering problems across the sort of full spectrum of physics. So you can set up heat transfer problems, you can set up structural mechanics problems, fluid flow problems, mechanics problems, and also acoustic problems, which is what I'm going to be focusing on in the webinar today. When it comes to simulating these engineering problems, we can look at a single branch of physics in isolation. So we can set up, for example, a simulation which deals entirely with acoustic modeling, or we can set up what we would call a multiphysics simulation, where we will couple together different branches of physics within a single model. And this can all be done within a single modeling environment. So the example that I have here on the slide is a loudspeaker. So we can actually set up this loudspeaker simulation all the way from looking at the magnetic field that's generated by the voice coil that will give us a force that will induce the mechanical vibration within the speaker structure and the speaker cone. And then we can look at how that mechanical vibration is going to lead to propagating sound. So we can actually capture all of the interacting physics phenomena within our simulation. And the idea behind this model, multiphysics modeling approach, is to be able to increase the accuracy and the fidelity of our simulations by capturing all of these physical interactions, essentially to make our simulations more realistic and better replicate reality. Now, in terms of acoustic modeling, we have a sort of general purpose acoustic modeling tool that will allow you to simulate across a fairly broad set of different acoustic applications. So you can model, I guess, what I would describe as kind of classical acoustic problems, which in the kind of COMSOL terminology, we refer to as pressure acoustics. So here what we're doing is solving the wave equation for the propagating pressure field within a fluid. We can also look at the equivalent in solids. So we can look at waves propagating in solids, or we can look at mechanical vibrations. The distinction between the sort of pressure acoustics and elastic waves is that when we're looking at waves propagating in solids, we will have both shear and pressure waves that we will be resolving. We can combine the pressure acoustics with the mechanics and mechanical vibration to model acoustic structure interaction problems, or if you prefer, vibroacoustics. And we can implement this as a bidirectional coupling. So what we can look at is how a mechanical vibration will generate sound, if we want to look at something like a loudspeaker or machinery noise, or we can look at how an acoustic signal will induce mechanical vibration. If we wanted to understand, for example, how something like an explosion might induce mechanical vibrations, or we might simply want to look at sound transmission through a partition or through a wall. We can also look at aeroacoustics, so looking at how acoustics will interact with flow. We can really look at aeroacoustics in one of two different ways. We can look at how flow will affect how sound propagates. So we will get a convective effect due to a background flow. So if our sound is propagating with the flow, we will tend to get an increase in the wave speed. If it's propagating against the flow, we will tend to get a decrease in the wave speed. So that's one form of aeroacoustic problem we can consider. We can also look at something called flow-induced noise, which is actually understanding the sound that's being generated by a fluid flow. So looking at, say, turbulent flow and the sound that that turbulent flow will generate. We can also look at something that we call thermoviscous acoustics. And this is relevant when dealing with very small, microscale acoustic applications. As we decrease the size of our domain in which our waves are propagating, we will find that thermal and viscous losses become proportionally more important. And we need to explicitly account for these thermal and viscous losses if we want to be able to accurately simulate the acoustic problem. And this would be relevant for looking at things like loudspeakers and microphones that might go into something like a handheld device or a mobile phone. We also have functionality that is designed for looking at modeling of ultrasound. So looking at modeling high frequency acoustic applications. And this functionality is for looking at the applications in the time domain. So looking at ultrasound and calculating it in the time domain. We have functionality for looking at large scale acoustic problems, what we would refer to as geometrical acoustics, for looking at modeling architectural acoustics, for underwater acoustic problems, and also for environmental acoustics. We have functionality for pipe acoustics, so essentially a 1D acoustic solver. And we have additional multiphysics functionality beyond sort of acoustic structure interaction. So these include things like acoustic streaming, where we might want to understand a flow that's being driven by a continuous acoustic signal. This is used in things like drug delivery, and also for looking at modeling of transducers. So these can be things like loudspeakers or underwater sonar transducers and things like that. And these can be electrostatically actuated or can be electromagnetically actuated. So this gives an overview in terms of the kind of acoustic modeling functionality. For the webinar today, what I'm largely going to be focusing on, though, is the functionality within pressure acoustics and also talking about modeling of geometrical acoustics. So as well as having access to a set of functionality that will allow us to simulate different types of acoustic problems, we will also have access to different numerical methods that we can use to study our acoustic problems. So this slide here gives you an overview of the different numerical methods that are available. So on the left-hand side, we have the finite element method and we have the boundary element method. So these numerical methods are based on us tessellating our geometry with a mesh and computing the solution to our acoustic problem on the nodes within our mesh. The nodal points will be distributed at the element vertices and also midway along element edges, depending on the type of element that we're using. But the key thing here is that we are using this mesh that we apply and tessellate the geometry with. And when we work with one of these methods, what we are simulating the acoustic problem as is a wave problem. So what that means is that our solution, once we've computed it, will look something like this. So we will get a map of our acoustic pressure throughout our modeling domain. The distinction between using the finite element method and the boundary element method relates to how we will mesh the geometry and then how we will compute our solution. So when we work with the finite element method, we will generate a volume mesh within our fluid medium, and we will compute the solution within this volume mesh. When we work with the boundary element method, what we will actually set up is a surface mesh on the surfaces of our geometry, where we have reflections and we have surfaces which are radiating, and we will actually compute the solution based on this surface mesh. When working with the boundary element method, we can actually still recover the solution throughout the volume, even though we compute the solution only on the surfaces, because we can actually extrapolate the data within the volume, even though we've used just a surface mesh and computed a surface-based solution. We then have the ray tracing method. So when working with the ray tracing method, essentially what we're calculating is we're calculating the trajectory of a set of rays and how they will move over time and interact with the walls of our acoustic domains. So essentially what we have is we have a set of particles and we track the trajectory of these particles over time. You can consider each of these particles as representing a wave packet, and we're actually tracking the trajectory of these wave packets over time. And we can also evaluate quantities associated with these wave packets, such as the intensity and the power that we associate with them, and how this will evolve over time, how the intensity will decay over time. We then have something that we call the discontinuous Galerkin finite element method. Now, this is a variation on the conventional finite element method. And the way that this numerical method will compute our numerical problem is based on a matrix-free implementation. Now, when we solve a numerical problem using the finite element method, as part of our solution process, we will have to invert a large system matrix. And this is, from a computational point of view, the expensive step in that solution process. So when we work with the discontinuous Galerkin finite element method, because we don't have a system matrix and we don't have to invert the system matrix during the solution process, we can actually compute the acoustic problem using less computational resources. So we don't need to use or access as much RAM during the solution process, which means that we can compute larger acoustic problems using less RAM. And this method is a method that we can use for solving large acoustic problems in the time domain in an efficient manner in terms of the computational resources required. So we have these different numerical methods that we can use. And we can also, within COMSOL, set up hybrid simulations where we will combine these different numerical methods in a single model, where we can essentially leverage the benefits of using these numerical methods in different regions of our geometry, essentially to kind of get a best of both, if you will. So this may commonly take the form of, for example, using a finite element model to create a high fidelity simulation of our acoustic source, and then to understand how that will lead to sound propagation over long distances, we may couple that finite element method model of the source with a ray tracing model that will allow us to then look at the sound propagation from this acoustic source. We can also set up hybrid models that combine the finite element method with the boundary element method. So that's an overview of the different numerical methods that are available. Now, when we're working with finite elements and we're working with boundary elements, we are simulating our acoustic problem as a wave problem. And when we simulate a wave problem, we need to ensure that we sample the wave at a sufficient number of points in space in order for the solution that we compute to be accurate. So we have an image here on this slide of a typical mesh. So this is a finite element mesh. And what we can see here is that in order to get an accurate solution in terms of resolving the propagating field, we need to have a minimum of 5 mesh elements per wavelength, assuming that we're working with second order elements. So this meshing criteria will ensure that when we compute our solution, that we sample it at enough points in order for the numerical solution to give us a good account of the real solution of the propagating field. Now, in the image below, what you can see is a plot where we've undersampled the solution. So what we have here is an image where we only have 3 elements per wavelength. And if we compare the blue line with the red line, we can see that by undersampling, we're actually introducing quite significant numerical error. So to avoid introducing numerical error, we need to use 5 mesh elements per wavelength. Now, as we increase the wavelength, as we increase the frequency, we will tend to decrease the wavelength, which means that our mesh elements will get smaller. And then we will need more mesh elements to tessellate our geometry. So as we increase frequency, we reduce the element size, we increase the number of mesh elements, we therefore then also increase the computational cost of computing our solution, because the cost associated with our simulation will depend on the number of elements that we have in our mesh. So what we will tend to find is that we will reach a limit in terms of the computational resources that we have access to in terms of frequency, where we can use the finite element method or the boundary element method and simulate the acoustic problem as a wave problem. And this is why we have access to other numerical methods that will allow us to go beyond the limits of using finite elements or boundary elements and simulating our acoustic problem as a wave problem. Now, when working with either finite element modeling or boundary element modeling in COMSOL, we use something that's called physics-controlled meshing. Now, what this means is that you provide the maximum frequency that you want to compute, and you define the fluid medium in which the waves are propagating. And from this, COMSOL will calculate the minimum wavelength. And it will mesh the geometry using the minimum wavelength to ensure that you will have 5 elements per wavelength, and you're satisfying the criteria that the mesh resolves the wavelength. So this process is automated in COMSOL through this physics-controlled meshing. If you're modeling absorbing layers because you want to model an open acoustic problem, you would typically model this using what we call in COMSOL a perfectly matched layer. In order to optimize the absorbing performance of a perfectly matched layer, we want the perfectly matched layer to have a structured mesh to optimize its absorption. And physics-controlled meshing in COMSOL will also automatically generate this type of structured mesh in your absorbing domain. So you will get a mesh that's optimized for performance in the PML. If you're modeling periodic problems, you will also get identical meshing on periodic boundaries. And if you're looking at calculating exterior fields, i.e. you want to extrapolate the solution outside of the computational domain, the physics-controlled mesh will also set up a matched layer of elements that will optimize the performance of this extrapolation process as well. So physics-controlled meshing will generate a fairly sophisticated mesh in terms of providing accuracy for your acoustic simulation. So in terms of the different numerical methods that we have access to within our acoustic modeling functionality. So when we're working at the sort of lower end of the frequency spectrum, we will tend to favor using the finite element method. So this is based on a volume mesh, and it will calculate a wave solution. We will find that as we increase the frequency, we will reach a limit to what we can practically compute using the finite element method. So in this kind of moderate frequency band here, we would typically favor using the boundary element method. So rather than having a volume mesh tessellation here, what we're setting up instead is a boundary mesh, which lowers our meshing requirements. Then when we get to higher frequencies, and we're in the high frequency limit, we would tend to use ray tracing or the ray acoustics approach. The use of frequency here as the determining factor, whether we are working with finite elements, boundary elements, or rays, is a little bit of a misnomer. The important metric is actually the ratio of your wavelength to the extent of your geometry. So if your geometry is, say, up to 10 to 20 wavelengths, then we would typically consider this to be a small acoustic problem that can be computed using the finite element method. If your wavelength, if your ratio of wavelength to geometric extent is, say, 20 to, say, maybe 50 or 100 wavelengths, then you would tend to be in this kind of moderate region. Then once we get to geometries which are more than 100 wavelengths in extent, then we are in the sort of high frequency limit where we would tend to favor using ray acoustics. And the reason for switching to using ray acoustics is because the computational cost of solving it as a wave problem becomes increasingly expensive, and it becomes impractical for us to compute it as a wave problem. In an ideal world, we would always use a wave formulation, but we don't necessarily have the computational resources to be able to do that. So the ray tracing approach allows us to overcome those limitations of working with a wave formulation. So in terms of numerical methods available within the acoustics modeling functionality, you can see here that we have finite elements, discontinuous Galerkin finite elements, boundary elements, and ray tracing. The largest set of functionality is implemented for the finite element method. So you can model pressure acoustics in the frequency domain and time domain. You can model waves in solids and porous materials. You can also look at things like aeroacoustics, thermoviscous acoustics, and pipe acoustics. With the discontinuous Galerkin finite element method, you can work only in the time domain. This can be in fluids or solids. This can also include nonlinear acoustics and can include the convective effects of fluid flows. For boundary element modeling, you can work with pressure acoustics, but this is limited to working in the frequency domain. And then for the ray approximation, you can work with ray acoustics, and this is limited to the time domain. So in terms of resolving our wavelength, we can see here that the number of elements here is going to be proportional to the wavelength. And here we have a power which is determined by the dimension in which we're modeling. So if we're modeling in 3D, then we have here something that is increasing with a cubic power. So that is to say that if we're working with a wave-based method, finite element or boundary element, if we were to multiply our frequency by a factor of 5, then what we would find is that we would have an increase in the number of mesh elements of a factor of 125. So it would be 5 cubed if we're working in 3 dimensions, that is. So we can see from this how increasing frequency will reach a limit in terms of what we can compute practically using the finite element method or boundary element method. Now, undersampling the solution, i.e. coarsening the mesh with respect to the wavelength, isn't really an option because it will introduce numerical error. So we can see here in the images here the effect of coarsening the mesh. And we can see that once the mesh is this coarse, that the solution that we get doesn't really look anything like what we expect it should. So coarsening the mesh isn't really an option here, but what we can do is we can switch to using a ray approach rather than a wave approach. So in terms of what we gain from using a ray approach, it will allow us to consider acoustic problems that are much larger in terms of the ratio of the number of wavelengths to geometric extent, but we will also lose some detail from our results as well. And essentially, the cost of switching from waves to rays is that when we're working with a ray approach, we won't be able to account for any diffraction effects within our acoustic field. So we won't be able to see these diffraction effects around objects. Now, if we're looking at modeling an acoustic problem where our geometric features are smaller or our geometric features are larger or much larger than our wavelength, then the effects of the diffraction should be negligible. So if our acoustic simulation is such that our geometry and our geometric detail is larger than our wavelength or much larger than our wavelength, then a ray approximation should be appropriate. So in terms of our sort of underlying governing equations that we compute, when we solve a wave problem, this is our sort of governing equation that we will solve for pressure acoustics. So on the left-hand side, you can see we have a wave equation, and on the right-hand side, we have it transformed into the frequency domain, and we have Helmholtz equation. So what we will compute is we will compute the acoustic pressure, and we need to provide some properties of our fluid medium, which is our density and our speed of sound. And we have a term here which will describe how our pressure will vary in time. And we have a term here which will describe how our pressure will vary in space. And we can add some source terms. So we will compute for the acoustic pressure at each of the nodes within our mesh. We can transform this equation into the frequency domain to remove the time derivative term and replace it with an angular frequency term. So this equation can be computed in the time domain, or it can be computed in the frequency domain. When we solve a ray acoustics problem, we solve a slightly different equation set, or very different equation set. Rather than computing for a discrete pressure on a fixed mesh, what we're actually doing here is we're calculating some quantities associated with each of these particles, which represents these rays, which are traveling through space and interacting with the walls of our geometry. So what we have here is we have a set of partial differential equations that we solve for each of our rays, where we have a wave vector, or the direction our wave is traveling, and we have a position vector here that we will compute. And we will relate these to the rate of change of the angular frequency and the rate of change with respect to time. So when we're solving ray acoustics, for each of our rays, what we will compute is a set of 6 dependent variables. That will be the position of the ray in space and the direction that the ray is traveling. We can also assign additional quantities that we may want to calculate within our rays, such as the intensity or the power. So we can add additional auxiliary variables to these rays as well. And this formulation that we use is called a mixed time frequency formulation. The benefit of using this type of formulation is that we can incorporate frequency-dependent boundary conditions. So the absorption characteristics of our boundaries can be defined with respect to frequency. In terms of analysis types that you can run, the main analysis types for acoustic modeling are doing a frequency domain study or doing a time domain study. So we can assign a frequency to our acoustic source and sweep through a range of frequencies in the frequency domain, or we can compute this as a time-dependent problem. We can also run an eigenfrequency study that will allow us to calculate resonant modes and resonant frequencies. And for a method called the statistical energy equation, which is available in COMSOL, we can actually also compute a stationary study. This will provide us with a steady state energy distribution from a continuous acoustic source. This is available only for closed acoustic problems. And this is actually a method that's used a lot in architectural acoustics. It's a very quick, lightweight way of doing an acoustic analysis. Okay, so I've talked about the different numerical methods that are available and a little bit about when these different numerical methods can be applied. What I'm going to do now is I'm going to actually put this into the context of the COMSOL software. So I'm going to show you how you can set up a wave problem and how you can set up a ray problem within COMSOL. And it's convenient to use a room example as the case study for demonstrating these different methods, because in a room, we can actually use a wave or ray-based method depending on the frequency of our acoustic source. So when we're working at low frequency, where the response of the room is largely resonant, we would typically favor using a wave-based approach. But once we get to higher frequencies, where we're dealing with a response which is more reverberant, then we would tend to favor using a ray-based method, because we can use a ray-based method. So the first model that I will show you here, I will actually build it from scratch for the benefit of those of you who are unfamiliar with COMSOL and haven't seen the software before. So I'm going to build this as a finite element model, and I'm just going to set this up on a simple room geometry. We have some objects within our room. It's a very sort of idealized and simplistic geometry, but it will demonstrate the method. So we have some absorption characteristics for the carpet, the sofa. The rest of the walls of the geometry will be modeled as rigid boundaries, i.e. perfectly reflecting boundaries. And we have an acoustic source here that will be specified using an acceleration. And this will be computed at a frequency of 200 hertz. So I'm going to come out of the slides and I'm going to move across to the COMSOL software. So when you load up the COMSOL software, this is the first screen that you see. And what I'm going to do here is I'm going to choose the model wizard option, which will ask me to choose the modeling dimension that I want to use, the physics that I want to include in the simulation, and the study type that I would like to use. So I'm going to select Model Wizard. I'm going to build this as a 3D model. And then I'm going to go to acoustics because I want to set this up as an acoustic model. Now I want to model this using pressure acoustics, and I want to use a finite element implementation. Now, the numerical method that you want to use to simulate the problem will actually be determined by what you select at this stage in the modeling process. So I'm going to select here pressure acoustics frequency domain. So this is a finite element implementation, and it will compute in the frequency domain. The boundary element implementation is here. And if we wanted instead to use a ray tracing approach, that's available here. So I'm going to add pressure acoustics frequency domain. The next thing I'm going to do is I'm going to choose my study type. So I'm going to select a frequency domain study, and then I'm going to select done. Now, once I've made these selections, it will take me into the COMSOL graphical user interface. And I have here on the left-hand side what we call, I should say, the model builder. So this lays out your modeling steps in the order that you would typically complete them. So you can define some input parameters. You can either build a geometry or import a geometry. You then assign your materials. You would set up your inputs or boundary conditions for your acoustic problem, generate your mesh, compute your solution, and then you can analyze your results. Now, to save me a little bit of time here, I'm going to import a geometry rather than building it. So I'm going to use the import option. And I'm just going to navigate to the file, and I'm going to import it. Okay. So I have my geometry that's been imported to the model. Now, if I go to my materials node, I need to assign the material that will occupy the internal fluid medium. And for this simulation, that fluid is going to be air. Now, when I add a material, I can add it either from a library of predefined materials, or I could type in the material properties myself. So I could set my own density and speed of sound. But air, as you might expect, is actually a predefined material in the library. So I'm just going to open up the material browser, and I'm going to add that material to my model. So I've added my material. The next thing I need to think about is how do I want to define the boundaries of my acoustic domain? Now, I want this to be a closed acoustic problem, so no open boundaries. So I'm going to set up a set of reflecting boundary conditions. And one of the boundaries of my acoustic domain, I'm going to set up as an acoustic source. The acoustic source is intended to mimic the behavior of a loudspeaker. So it's going to be a mechanical source defined with a mechanical motion. So if I just go back to my model here, if I right-click on the pressure acoustics node, it will provide me with a set of inputs that I can select from. So the first thing I'm going to do is I'm going to add my source condition, which I'm going to set up using an acceleration. I'm going to turn on wireframe rendering just to make it a little easier to see it. So I'm going to set this acceleration as 100 meters squared per second. And this is going to be constant at the frequency I specify. For the remaining boundaries, I want some of them to be perfectly reflecting, but I want some of the boundaries to have some absorption. So the default boundary assignment is sound hard, which essentially will operate as a perfectly reflecting boundary condition. So I can leave that on the majority of my boundaries. But for the others where I want to account for some absorption, I'm going to add an impedance boundary condition. When it comes to setting the impedance, we can set it as a complex impedance. You can also set it as a frequency-dependent impedance, so we can have different impedance values for different frequencies. We can also select from a set of sort of empirically defined boundary impedances for things like physiological materials like skin or the human ear, for porous layers like carpet or things like that. Or I can simply set this using an absorption coefficient, which is what I'm going to do here. So I've set my boundary impedance for the carpet here. I'm going to add a second boundary impedance for the sofa here. I'm just going to select all of these in one go, and I'm going to define this using an absorption coefficient. Okay, so I've set up my boundary conditions. I have set up some impedance. I've set up a set of boundaries which are going to be rigid. And then I have my acoustic source. So what I can do now is I can move on, now that I'm happy my acoustic problem is configured as I want it, to the meshing step. Now you'll notice here, this is where we have our physics controlled mesh. Now to be able to use the physics controlled mesh, I actually need to go to the study node first and set the frequency, because this is needed for the software to be able to calculate the wavelength and then to be able to distribute 5 elements per wavelength. So what I'm going to do here is I'm going to set my frequency, and then I can go back to my mesh node and hit build. So this is essentially going to mesh my geometry with 5 elements per wavelength, but the mesh must also conform to all of the geometric detail as well. So some of the detail here in the geometry may be even smaller than that fraction of a wavelength, but the mesh must conform to that as well. Okay, and then I can go to the study node here, and I can run the simulation and compute my solution. So I will get a result. So I have my acoustic pressure throughout my room, and I also have my sound pressure level throughout my room as well. Now, I just quickly want to show something here in terms of the mesh. So what I'm going to do is I'm going to plot the mesh and cut away the mesh. So on the mesh node, I'm just going to plot it so that we can see it. And then I'm just going to cut away so that we can see what the mesh looks like in the interior. So if I just do this, we can clearly see that this is a volume mesh because we're solving this using the finite element method. So we have this sort of volume tessellation, and we compute our acoustic pressure within this mesh. Now, in reality, in a simulation like this, you wouldn't necessarily just compute a single frequency. What you would actually do is compute something like this. So although in the model that I computed there, I set only a single frequency, and that was really just to save some time, what you can actually do here instead is you can actually run for a frequency sweep. So we can sweep through a frequency band and understand the response in that frequency band. We can use a linear step, or if you prefer, we can use a logarithmic step if you want to step by octaves, for example. Now, we can also do things like insert a microphone at a particular location. So what we can do is essentially take a point within our model, insert a microphone at that location, and we can look at how the sound pressure level varies with respect to frequency at that location within our room. So this is a sort of typical model that we might set up here as a finite element model of a room acoustic problem. Now, if I go back to my model here, I've computed this at a frequency of 200 hertz. Now, if I go to my solver here, this will give me, in terms of the number of degrees of freedom, so the number of variables that we are solving for here is 36,000. And this number of degrees of freedom is going to determine how large our acoustic problem is in terms of the computational resources that are needed to compute it. Now, 35,000 is a fairly small number, and we can see here our solution time is only 7 seconds. So at this frequency, we are in the regime where the use of the finite element method is appropriate and is going to give us a high fidelity result at fairly low computational cost. If now I was to say, want to study this acoustic problem not at 200 hertz, but instead I wanted to switch to solving it at 1 kilohertz, if I go back to my mesh node here and rebuild my mesh, what we will clearly see here is that the level of mesh resolution has been drastically refined in order to resolve this much shorter wavelength. So we had 36,000 mesh elements and 36,000 degrees of freedom at 200 hertz. What we will see now is that we have somewhere in the region of about 2.5 million mesh elements and 2.5 million degrees of freedom. Now, if you have the resources available to you, you could conceivably compute this model using, say, HPC computing or something like that, but it would be a heavy simulation to run. So this is where we can consider switching from using a wave-based solution that's either finite element or boundary element based to using a ray approach instead, because it provides us with a more favorable method in terms of the computational cost of computing. So the number of elements now here is up to 2.7 million. If I go to the statistics here, we will see that that number of elements is similar to our number of degrees of freedom, because we have a single degree of freedom here. No, sorry, I tell a lie. So that's 3.6 million degrees of freedom. So we have now a fairly large computational problem. Now, in terms of comparing a finite element model with a boundary element model, I have here the boundary element equivalent of the model that I've just set up. Now, the setup of the problem here is very similar. We assign the boundary elements to our domain. We set up some boundary conditions for our impedance and our radiating surface. The difference between this model and the previous model relates to how it's going to be meshed. So if I hit plot here, and if I set up an element filter again, what we can see is that the mesh this time is just a surface mesh. So we're meshing the boundaries of the geometry. However, we can actually recover the solution throughout the modeling domain, despite only solving it on the surface, by adding this grid on the results side. So what we can do here on the results side is we can set up a volumetric grid and extrapolate the data throughout that grid. So we can still get a volume solution despite only solving on the boundaries. And this can allow us to push up further in terms of the frequency. Then finally, I have the ray approach here. So in terms of building up this model as a ray model, if I just go back to the menu at the start, I would select your model wizard, 3D. Under acoustics here, I can select from geometrical acoustics, ray acoustics this time, rather than pressure acoustics, and add that. And this is what our ray acoustics interface would look like. So for solving the ray acoustics, we need to set up some conditions for our boundaries as we have in the previous scenarios. So we set up some impedance or absorption coefficients on the boundaries. But our acoustic source this time is defined using what we call a release feature. And this release feature in the model that I've set up here is set up just using a sort of classical release where we have a hemispherical release, which has uniform directivity in all directions. So we have this hemispherical sound source that's being released from this location here, and it's being released with equal intensity in all directions. We can also define this release using information generated by a finite element model if we wanted to couple ray acoustics to finite element modeling. But for this simple model, I've just used a sort of academic type release feature. So we set the number of rays. So the number of rays here is set to 8,000. And our number of degrees of freedom in the ray problem will be dependent on the number of rays multiplied by the number of dependent variables. So we have our ray position and our wave vector. So 6 dependent variables multiplied by 8,000. And then we can also compute additional quantities on our rays as well, such as the intensity and the power. So this is adding additional dependent variables. But if we go to the compile equations here and look at the statistics, we're still solving here a fairly modestly sized computational problem. So 144,000 degrees of freedom. Now, when solving the ray problem, the results that we will get will look very different to solving it as a wave problem. So this is what we can see. So we can see here, this is a plot of the ray trajectories and the intensity of the rays. And we could see how this evolves over time. So we can look at a very early time step, and then we can see how this spreads and evolves over time. We can also output architectural metrics quite easily from a ray acoustic model, like impulse response and things like energy decay over time as well. Okay, so that's just a very quick overview of setting up a wave-based model and setting up a ray-based model. Now, I mentioned earlier in my slides that the ray approximation holds when the geometric detail is much larger than the wavelength. This is true, but when you're working with closed room acoustic type problems, there's also another metric that we can use to determine whether we are in the regime where a wave formulation should be used or in the regime where we can use the ray formulation. And this can be evaluated using what's called the Schroeder frequency or the Schroeder cutoff frequency. And this will be dependent on the density of the number of modes within the room. So essentially identifies the transition from a modal dominated behavior to a reverberant dominated behavior. Now, I had intended to go through some slides on this, but I'm conscious of my time, so I'm just going to move through this quite quickly. The form of calculating this metric can be easily found online in the literature, available online or in any engineering textbook. But we can essentially use the Schroeder frequency to be able to determine when the ray approximation is appropriate for our room acoustic modeling. And in practice, this frequency will tend to be, in most cases, somewhere between 200 to 500 hertz. So in terms of summarizing the different numerical methods available, we have the finite element method, first of all, which is good for small to mid-sized acoustic problems. The form of the system matrix in finite element problems is sparse. Now, this means that for the number of degrees of freedom, we actually can invert the system matrix quite efficiently because the matrix is populated largely with zero values. So although it's a large matrix, from a computational point of view, it's actually quite inexpensive, relatively speaking, to invert this type of system matrix. We also have a large number of multiphysics couplings for the finite element method within the COMSOL software functionality. The drawback, however, though, is that we require a mesh throughout our modeling domain, and this mesh will scale quite badly with respect to frequency in terms of the number of elements that are needed. We have a DGFEM method, which doesn't rely on a system matrix, so reduces the cost of the solution process. So it will allow us to compute larger problems with the finite element method. However, it's only available in the time domain. We then have the boundary element method, which is good for sort of mid-sized to large acoustic problems. We require a mesh only on surfaces. And again, we can set up multiphysics problems using the boundary element method. So we can couple this to mechanics, for example. Some of the drawbacks here are that it's only available in the frequency domain. We cannot consider a graded media. So this means that the speed of sound throughout our modeling domain has to be constant. We can't have a variation in the speed of sound, which would tend to create a kind of curvature or refraction in our propagation. Because the system matrix that is generated by the boundary element method is dense rather than sparse, it's actually expensive per degree of freedom. So we can't directly compare the cost of computing with the finite element method and the boundary element method based on the number of degrees of freedom, because the boundary element method is more expensive per degree of freedom. And then finally, we have the ray tracing method. So this will be useful for looking at large to very large time domain models. So underwater acoustics, architectural acoustics, and also environmental acoustics. The drawback here, though, is that we will get less physical information in our results. So essentially, it's a lower fidelity approach, but allows us to go to larger geometries or higher frequencies. Okay, so before kind of moving on to the short break, I just quickly want to say a few words on hybrid methods. So as well as working with one of these different numerical methods within our simulation, we can also set up simulations that combine these different numerical methods, essentially allowing us to leverage the benefits of these different numerical methods by assigning them to different domains of our geometry. And these couplings can be set up within the kind of COMSOL software user interface. So the first example I have is looking at modeling an open acoustic problem. Now, one way that we can do this is by combining a finite element method formulation with a boundary element method formulation. So the example I have here is an open pipe. So what we have is we have a sort of oscillating piston here at the bottom of the pipe, generating propagation along the pipe, and then we want to model this infinite environment outside the pipe. So we want to allow the field to propagate to infinity. Now, of course, in reality, it's impractical for us to try and model an infinitely large domain, so we need a means of truncating the modeling domain. So we could model the solution in the near field as a finite element problem, and then model the propagation to the far field as a boundary element method problem. So rather than building this from scratch, I'm just going to kind of open this up and show what it would look like in the context of the software itself. So if I just go back to the model wizard steps, the process for building a model like this would involve first selecting the modeling dimension, which in this case is 3D. And if we want to combine different numerical methods, we can actually select more than one of these, what we call physics interfaces, at this stage in the modeling process. So what I would do is add, first of all, pressure acoustics frequency domain, which is a finite element formulation. And then second, I would add boundary elements, pressure acoustic boundary elements, which is a boundary element formulation. And I can couple these two together. Now, if I just go to the model here, what I have is I have my model, which benefits from symmetry. So rather than the full 3D geometry, I've modeled only 1/4. The material assignment here is going to be air, but you'll notice that air is added twice. Now, the reason for that is because we need to add air to the volume here, or the domains, which are used in the finite element formulation. But we also add air to this void region outside of the domains where we have our mesh. So we want to assign a material to this region, which we are not actually meshing. And this region here is what we will evaluate via the boundary element method. So this is essentially the material assignment for the boundary elements. And we assign it to what's called an infinite void. That's just an infinite region outside of the modeling domain. In terms of setting up the acoustics, we have the finite element interface assigned to the domains where we're meshing. We have a boundary condition here, which will operate as our acoustic source. And then in the boundary element formulation, we assign that to the infinite void. We also add some symmetry planes here for the boundary elements. For the finite element, the sound hard boundary is actually the equivalent of a symmetry condition, so I didn't bother including that as well. Now, the key thing here is how we couple together the finite element formulation with the boundary element formulation. And when we stack more than one of these nodes in the model builder, we will very often get this multiphysics node, which will provide us here with an option to couple together the different physics interfaces that are here. So this acoustic BEM-FEM boundary will take care of the coupling. And essentially what it's going to impose is that we have a pressure continuity as we transition from the interior finite element domain to the exterior boundary element domain. We can then compute our solution, and we can recover results in the interior computed using the finite element method. So this is our finite element solution. And then we have the solution in the exterior, which is our boundary element solution. Now, when working with the boundary element method, because we have to extrapolate the data points, some of the heavy lifting in terms of generating the results is actually done on the results side. So you'll notice that some of these plots will take longer to generate because the data isn't already available. It needs to be generated. So we can see here that we have this solution computed outside of the modeling domain with boundary elements. And in terms of setting the size of this grid, I can make it as large as I want to make it. And then I can also distribute a set of points within that grid where we will extract the data. And then I can also do things like understand the far field radiation pattern using the BEM solution. So this is looking at the radiation pattern at a distance of 10 meters. So what we're looking at here is essentially sweeping through the angles here in front of our geometry and measuring the sound pressure level at a distance of 10 meters. So we can see that it looks something like this. So that is a coupling of the boundary element method with the finite element method. If we wanted also to couple the finite element method to ray tracing, that's something that can also be done. So when working with ray acoustics, we will typically be looking at propagation over large length scales. But we might also want to consider a high fidelity model of our acoustic source. It could be a loudspeaker, for example, like this. This is a table loudspeaker. So what we can do is we can essentially create what I would call a multi-scale model and then combine the different numerical methods. So we use a small scale, high fidelity model, which is computed using the finite element method to evaluate the acoustic source. So we will get the intensity and we will get the directivity. And then we can import that data into a ray acoustic simulation to then simulate how that sound will propagate using the ray approximation. So I have an example here, which I can open up, which demonstrates how all of this is set up. Now, all of the models that I'm going to show you here are actually available on our website if you want to refer back to them later. So what we have here is we're looking at a car cabin, the interior of a car cabin, and we have a high fidelity model of our source, which is a tweeter on our dashboard. So this is a finite element model that's set up. And then we look at how that propagates the sound into the car cabin using ray tracing. So we have features available that will easily allow you to set up this coupling. So we have our FEM submodel, which will provide us with the acoustic intensity and the directivity, i.e. the direction in which the sound is propagating and with what intensity. And that's then ported over to our ray tracing model and is used to define our acoustic source. So we can get a simulation that looks something like this. So I'm just going to come out of the slides again and just come across here. So this is a simulation here. So we have a component here, which is actually set up using an axisymmetric finite element model of the loudspeaker here. And we use this exterior field calculation essentially to calculate the acoustic intensity and the directivity on the exterior surfaces here of our finite element model. We can then use that in a ray tracing model to set up a release condition. So this release condition will essentially extract the data from the exterior field that's been evaluated using finite elements. So we have a sort of high fidelity finite element model of the acoustic source, like so. And then we can look at the ray solution of how this acoustic source will then propagate within this enclosed space, this enclosed environment of our car cabin. The plots, yeah, okay, so we can get something that looks like this. And in terms of the model setup, it's a little more complicated than the model I showed you of the room, but the increased complexity here is really just down to setting up different sets of absorption conditions on the different boundaries of the geometry. And of course, from a geometric point of view, it's more complicated. The last kind of method that I just want to quickly mention is that when solving for building acoustics or room acoustic simulations, we can use a hybrid approach where we will solve for the field using a wave-based approach at low frequencies and then transition to using a ray-based approach at higher frequencies. So this, again, is just a simple demo example where we have a simple point source within a room at low frequencies below the Schroeder frequency, where we will not necessarily get an accurate solution using rays. We will favor using a wave formulation. So we can solve that for the low frequencies up to 500 hertz. Once the computational cost of this wave-based method starts to become considerable, then we switch over to using a ray-based approach. And we can bring these results together so that we are able to combine the data and look at the low frequency based results calculated with a wave-based finite element approach and also the higher frequency data, which is calculated using a ray-based approach. We can also do things like calculate the impulse response over time as well. And the method that we use to transition from the data generated by finite elements to rays is we can use this filter. So we can use a bandpass filter here that will essentially provide a transition from the wave-based finite element solution to the ray-based solution. Okay, I suggest we just take a couple of minutes there just to have a comfort break. I'm conscious of my time, so I'm going to have to truncate the second session a little. But all the same, I suggest that we just take 2 minutes, 2-3 minutes there, and I'll start again at, say, 13 minutes past.
Pause the recording for now.
Okay, so let's move on to a different topic. So in this second section, the first thing that I want to discuss is modeling of porous materials. So I guess the first two questions are, what is a porous material and why do we want to be able to simulate a porous material? So a porous material essentially is a material that at the micro scale is composed of two phases. We have a solid matrix material, and we have a set of pores distributed throughout that solid matrix material. So, you know, it looks something like this in 2D, and we have a sort of three-dimensional visualization of a porous material here. Now, the reason that we want to be able to model porous materials is because they're commonly used in acoustic applications. So porous materials are often used for acoustic absorption. So we have things like rock wool, glass wool foams, and things of that nature. Soil and subsurface materials are porous, so naturally occurring materials that we might encounter in environmental acoustic problems. In architectural type acoustic modeling, you know, we have building insulation and masonry. And also in things like medical applications, biological materials like bones and tissue are also porous. Now, in terms of simulating a porous material, we don't, of course, want to include all of the complex pore detail. So meshing something like this will simply just generate so many mesh elements that we want to avoid, if possible, having to go to actually modeling all of the pore detail. So what we essentially use when modeling porous materials is a homogenization approach. So essentially we will average the pore properties across the domain and instead model the porous material just as a continuum. And we can account for the pore structure within this continuum using a set of material properties. Now, these properties include things like porosity, which is the sort of void ratio of pore to matrix material. We have permeability, which is essentially resistance to flow through the material. We also have things like tortuosity. So this would essentially determine how much longer the path would be through the porous material versus just a straight path right through the material. So it has to take a more circuitous route. That's kind of the tortuosity. So essentially we can use these material parameters to essentially approximate the pores across a continuum. In terms of modeling porous materials within COMSOL, you have access to two different methods that you can use. And these methods are based on sort of semi-empirical formulations. So the first approach that we can use to model a porous material is using what's called an equivalent fluid formulation. What this means is that we actually model the porous material as a fluid which has significant attenuation within it. So we calculate this only as an acoustic pressure. Now, in terms of computing the acoustic problem, this provides us with the most efficient method for modeling a porous material in terms of it being low cost, low computational cost. The alternative method for modeling a porous material is to use what we call poroelastic waves. So in this case, what we're essentially modeling is an acoustic structure interaction problem. We're calculating the vibration of the pore matrix, the porous matrix, but also calculating the acoustic transmission within the pores. So this is essentially an acoustic structure interaction coupling that's set up within a single domain. So within that domain, we calculate the displacements, the mechanical displacements, and the acoustic pressure. Now, this method will give us a more high fidelity result, but that will come at increased computational cost. So more RAM and more degrees of freedom needed to simulate using poroelastic waves. The methods are based on the sort of bio theory in both cases. So we have these two different methods that we can use. So when it comes, first of all, to considering the first option, where we work with poroacoustics, what we would do in terms of setting up our problem is we would still work within the framework of a pressure acoustics physics interface. So we have the pressure acoustics node, and then we can add a poroacoustic material as a material type within that pressure acoustics node. And we can select from a set of different empirical poroacoustic models that we can assign to the model. Now, the equivalent models that we can choose from, so all of these different options here, what they will essentially implement is they will set the speed of sound and the density of the material to be complex, where we will add an imaginary term that will account for the attenuation within the material. And there will be different ways in which that imaginary term is formulated depending on the material model that we select. When working with poroacoustics, we're not solving anything in the structural part of the porous material. We're only calculating the acoustic pressure. So we need to make some assumptions about what the pore matrix is doing. So we can consider that the pore matrix is either limp, i.e. it has a very low stiffness and it will move with the fluid and in phase with the fluid, or we can consider the opposite extreme, that the porous matrix is rigid. And these are options that are available within some of our poroacoustics material models. Now, this table here gives you an idea of some of the properties that are needed to define these different sets of porous material models. So we have things like porosity, tortuosity, flow resistivity, which is somewhat analogous to permeability, density. And if we're going to model the mechanics as well as the acoustics, then we need to provide some mechanical properties for the matrix material as well, along with some damping characteristics for that matrix structure material. So I'm going to use another simple example here just to demonstrate how you can incorporate a porous material into a simulation within COMSOL. So what we have here essentially is an exhaust system. So this is looking at a muffler where we have some porous material included that's intended to provide some acoustic absorption. So this particular model is run for two different scenarios. One where we have a porous material included to provide some attenuation, and one where we have no porous material included, so that we can have a baseline solution that we can compare against. And the quantity that we're using here to understand the extent of the attenuation is the transmission loss. So what we're looking at here is the power in divided by the power out. And we express this in dB, so that should actually be 20 log base 10. If I go back to COMSOL here, so if I just select File and New, I'm going to select Model Wizard. This is a three-dimensional problem. I'm going to add the pressure acoustics and then select frequency domain. And rather than building the geometry here, I'm just going to insert the geometry from an existing COMSOL model file. Again, this is to save some time. So I'm just going to import the geometry. So I have my exhaust here. I then am going to assign the material to the exhaust. So I'm going to add air as the fluid in which the sound is propagating. Then if I go down to the pressure acoustics node here, If I right-click on pressure acoustics, I have the option to add poroacoustics. So I can select this option here, and then I can assign it to my geometry. So by virtue of me now designating this as poroacoustics, this will now be modeled as a porous material, and I can choose from a range of different poroacoustic models here. The model that I select will determine what material properties are needed in terms of defining that particular porous material. Now, if I just quickly open up the computed version, bear with me a second here. So I'm just going to open up the computed version of this model. I'm also going to open up some other files. So I'm just going to open up the model with the solution computed rather than building up the entire model. A few files. There's some of these as well. What's going on here? Okay, so apologies for this brief interlude. Too many things open. I tell you what, whilst this is opening, Anton, if you have the questions there, this is probably a good time for me to answer some of these questions whilst I'm just waiting for these files to open.
Yes, they are all in Q&A. Do you want me to read them?
If you could, sorry, it's not that easy for me just to switch over to looking at the...
So, John is asking, it was remarked that FEM is always preferable but limited by available computational resources, but also that the volumetric solution is still available from BEM. Given that, what is the advantage of FEM where it can be applied?
So that's a good question. So the boundary element method, because of it having this dense rather than sparse matrix, when you're solving for problems that are maybe only 1 to 2 wavelengths in size, for example, and you might have a geometry which has quite a complex topology, what you will actually find is that the boundary element method, in terms of the resources needed to compute, can actually be more expensive than using the finite element method for small acoustic problems. So it's only once you get to the sort of mid-sized to large acoustic problems that you will actually see the benefit of using the boundary element method. And that's why we will tend to favor using the finite element method at the lower end of the frequency spectrum. The other thing I would say is that in COMSOL, the set of features available for finite element modeling is richer than it is for boundary element modeling. So there's more options for the type of acoustic problem that you want to simulate and for boundary conditions and things of that nature as well.
Do you want me to continue, or are you ready to?
I think I'm ready to go here. So in the model I was just showing you, I was adding the poroacoustic material to my model here. You assign it to the geometry. You will select the poroacoustic model that you want to use. Now, if you have any doubts about which type of material these models should be applied to, I recommend referring to the COMSOL documentation. It has quite a lot of detail in terms of where these material models can be applied. So whether it's foam, glass wool, rock wool, and things like that, and also the frequencies over which they would be valid. So you would add this to the model. Now, in this simulation, the source is defined as a port, and we have a port at the opposite end to model an open boundary. So essentially what we have here is we have a field which is propagating into the inlet into the inlet pipe and out of the outlet pipe. And we can set this up using a port condition, defining the port in terms of the cross-section and also the power of the acoustic source. So this is intended to mimic noise upstream coming down into the exhaust. Now, if we look at the results here, what we can see is if we look at the transmission loss, we can compare the scenario with the porous material and without the porous material. So what we can see here is we can look at the case where we have no porous material, which is blue, and the porous material here, which is shown in green. So we get a much more significant transmission loss at most frequencies with the porous material, though there are a few actually which are sort of outliers. So this is one way that we can model a porous material using this poroacoustics node. Now, essentially, all this is doing, as I mentioned in the slides, is making our material properties complex. So there's not really much additional cost associated with using this approach versus modeling it just as a pure acoustics model. The alternative is to instead use the poroelastic waves option as opposed to poroacoustics. Now, this is the more high fidelity alternative where we calculate the mechanical response as well as the acoustics. And the step-by-step approach for doing this in terms of the first few steps that you would follow would involve going to Model Wizard, selecting that you want to model in 3D. The physics here this time would involve selecting pressure acoustics to model the non-porous part of the geometry. So we could add that. And then we would add a second node for the poroelastic waves, which would be computed in the porous part of the geometry. And we would couple these two together and set it up as a multiphysics model. So in the kind of COMSOL user interface, once this is all set up, it would look something like this. So we have the pressure acoustics assigned to the inner part of the exhaust manifold. And then we have poroelastic waves assigned to the exterior part where we're computing for the porous material. And we need to set up a multiphysics coupling between the acoustic part of the model and the poroelastic part of the model, which is a combined acoustic and mechanics implementation where we calculate the displacement and we also calculate the acoustic pressure. So this allows us to account for a scenario where we're not considering the porous matrix to be either rigid or limp. We can consider the intermediate regions where we're actually accounting for the stiffness of the pore matrix. And we may also see in our results some effects where we might get some resonances, mechanical resonances and spikes that we might not otherwise see if we were just using a formulation that was just pure poroacoustics. Now, in terms of choosing which of the poroacoustic models to use in your simulation, as I said, the COMSOL documentation provides a lot of information on where these different porous models can be applied. But in practice, the decision may actually come down to the information that you can get in terms of the material data. The Delaney-Bailey-Meeke poroacoustic model is probably the most commonly used, and that's because it only requires a single parameter in terms of defining it, and that's the flow resistivity, which can be easily obtained from material data sheets or from material suppliers. But kind of tying into this question about material parameters in order to characterize our porous material, if we don't know what those material parameters are, what we can actually do is we can use parameter estimation to actually inverse model this particular process. So what I mean by that is we can actually do some experimental work on a sample of our porous material in an impedance tube, for example. So we can set up an impedance tube experiment. We can use some microphones to measure the acoustic pressure versus our frequencies. And through parameter estimation, we can actually work in reverse to match the results of a simulation to our experimental data in order to work out what material parameters would be needed to characterize our porous material to match with our real porous material. And this is something that can be set up in COMSOL as well. We would just essentially replicate the experimental setup in a simulation, and using optimization, we would match the results from the simulation with the experimental results. And once they match, we know we found the material properties that we're looking for. And we have some models, or a model, I should say, that will demonstrate how you can set up and compute this process within COMSOL. In the model here, we're working with a Johnson Shampoo Allard porous material, which has 5 material parameters needed in order to define it. So we have flow resistivity, we have a thermal characteristic length, a viscous characteristic length, tortuosity, and our porosity. And we can replicate our impedance tube experiment in a simulation like this, and we can feed in our experimental data into the COMSOL model, match the COMSOL model to the experimental data by adjusting the material properties until it matches. And when it matches, we should have found those material properties that we are looking for. And once we've done this for a sample of material, we can then apply this to another model where we are using the same porous material in a different simulation. Now, in terms of my time constraints, I think I'm going to have to end there, but I'm happy to stay for a few more minutes to answer any remaining questions, Anton, that are in the chat. Now, I'll share with you a complete version of the slides, so you will have them as a reference. But for now, I think we need to go to the questions.
Yeah,
Yes,
I think I'll just add as well. I did respond to some of the questions, just saying that if we can't get to them, then they can send them via email. So yeah, so they might come up in the answered section, Anton, but yeah, I don't think they've actually been responded to, some of them.
I noticed this earlier. Yes, yeah. And I want to pass this on Robbie as well. So the next question, which wasn't answered, was from Hamad. Do you want me to read, Robbie, them?
If you wouldn't mind,
Yeah.
yes.
So when we say large, how large is it in terms of distance between source and receiver in outdoor acoustics, environmental acoustics?
So when working with the boundary element method, actually, you can model problems where there is a large distance between a source and a receiver, because you don't need to mesh the region in between. So that's actually another scenario where boundary element modeling can provide a computational benefit over finite element modeling. Because in a finite element model, we would have to mesh the region in between the source and the receiver, whereas in the boundary element method, we wouldn't. For a ray tracing problem, there isn't really a limit as such to the size of the acoustic problem that you can compute. But when we talk about large acoustic problems, we would probably be talking about something that's greater than sort of 20 wavelengths in terms of the distance or the extent of the geometry.
I think Jason's question was answered by Oli. Next is from Hamad. Also, when we combine two numerical model, does it decrease computational cost and time?
So if we were to say compare, so if we were to take the car cabin acoustic model that I briefly covered, if we were to compute that car cabin model using entirely a finite element implementation, then it would be more expensive and more time consuming to compute than using the hybrid approach, where we combine a finite element method implementation for the source with array acoustics implementation for the propagation. So it should be. Otherwise, the use of the hybrid approach becomes less and less favorable. We want to work with hybrid methods where they're going to provide us with a computational benefit.
The next question is from, I apologize for wrong pronunciation, Prachi, and it's about comparison of Galerkin method versus ray acoustics. And there are a few questions on that. First is, what is the time taken? And do you want me to follow your answers for the next question? Or?
So in terms of the time taken for a DGFEM model versus a ray acoustic model, if we were to solve equivalent problems using the two different approaches, because DGFEM is a wave-based approach as opposed to a ray-based approach, it will take longer to compute using DGFEM versus rays. However, the DGFEM method will present us with the opportunity to use a wave-based approach and compute it using less resources in terms of RAM and processor power than we would need if we were to compute it using a conventional finite element problem. So I think the key with DGFEM is that the cost is lower in terms of the resources needed to compute, but computation times will still be high in comparison to using ray acoustics.
Yeah, and then scale of model, I think you partially answered this in the distance between the source and receiver.
I mean, these numbers I'm saying will depend on the resources that you have at your disposal. Some users will have access to clusters, and therefore, they have access to significant computational resources. So their limits might be higher than the numbers that I'm saying. So really, the limits will typically be based on the computational power at your disposal.
Accuracy, it's I suppose again depending on.
So the accuracy of DGFEM versus rays.
Yes.
So DGFEM is going to give a higher fidelity result. So it should, or it will be more accurate. Although if you're working within the regime that the ray tracing method is appropriate, then it should be sufficiently accurate. But using a wave-based method will provide you with a higher resolution of result. So it will, in general, be a more accurate option.
Again, within the same question, ease of using impedance absorbing boundary for DGFEM and ray acoustics.
So the way that you would set this up in both cases should be the same. You assign it to your geometry and you set your input values. When working with ray acoustics, it's more straightforward to implement frequency dependence than it is in DGFEM. In DGFEM, we can do it, but you need to do a little bit of back calculation behind the scenes because we're working in the time domain rather than in the frequency domain. So we need to calculate some additional variables to be able to determine what the frequency of the approaching wave is. Whereas in ray acoustics, we actually define the frequency directly as an input, which can then be used to look up the material properties or the boundary conditions, I should say.
And suppose this all related then to your previous answers, which method is recommended for indoor and outdoor cases? Again, it's DGFEM and ray acoustics.
I mean, I would say that it will depend on problem size. I mean, although DGFEM, as I said, from a computational point of view, is leaner than conventional FEM, it's not a silver bullet. So it will still have a cost associated with using it. So for sort of large scale outdoor environmental acoustic problems, it will depend on the problem, but probably ray acoustics will be more relevant.
Then again, it's a question from Prachi, and is there a porous acoustic option in ray acoustics or DGFM?
There's not. So porous acoustics is actually only available for frequency domain modeling. So there's no time domain implementation, certainly for porous acoustics. The reason being is that the way that this is formulated is that it will define a complex speed of sound, and complex numbers don't really have any meaning when you're working with something in the time domain. So we need to be able to work within the frequency domain. And ray tracing and DGFEM are both time domain formulations.
Yes, and then it's suppose follow up again. This can absorptivity versus frequency be used instead in ray acoustics DGFEM?
It can be used in either. So you can set up frequency dependent boundary conditions.
How much more time is taking than porous acoustics is added in comparisons with narrow region acoustics? I suppose this is just for the pressure acoustics model.
So the cost should be comparable because essentially what they're doing is they're doing something very similar. In both cases, we're setting up a complex density and speed of sound. In one case, it's to account for the attenuation due to the pores. In the other case, it's due to the attenuation due to the viscous effects at the boundary and the thermal effects at the boundary. So ultimately, they're doing something very similar. So the cost of using them should be, I would say, equivalent.
Another question from Jacob: can COMSOL be used for optimization? So running many different scenarios with variation in certain parameters to get an ideal outcome.
Yep.
Achieving reverberation time with smallest area of absorbent finishes.
So you can run optimization analyses in COMSOL. So the parameter estimation method that I described is one form of optimization, but you can also do design optimization as well. So you can define an objective. That might be that you want as flat a frequency response as possible, or to maximize sound pressure level at a certain distance. These are all different objectives that you can set. You set your objective, and then you can define some control variables that can be adjusted in order to either maximize or minimize the objective. So these can be, to change dimensions of the geometry. You can also do things like shape and topology optimization if you want to as well.
Question from Porous: can you input materials as they sound insulation performance?
So I think what you would need to do in this case would actually be to reverse engineer the problem. I think what you would need to do is similar to the approach that I mentioned for the porous material. So essentially you have the target solution that you need to match, and then you can adjust the inputs to the simulation in order to match that set of target data. So I think you would need to run that using inverse modeling or parameter estimation.
Then a suggestion from anonymous attendee: would have been great if model analysis was explained.
Okay.
Do you have it in your slides, or was it part of your presentation?
So I did have a mention of modal analysis in the slides. I have a model here that I can open up quickly that has modal analysis. So to do modal analysis in COMSOL, you would typically use the eigenfrequency study option. So I have here modal behavior of a room, which is a building acoustics problem. So rather than using the frequency domain option or using the time domain option, what you would select when setting up the problem is the eigenfrequency option. You can set the number of modes that you would like to compute and where you would like to search. So if you set this to 1, you will typically get the lowest set of modes. And then you can run the analysis and you will get the acoustic pressure. Or you should do, no, this doesn't have a solution. So what you would get essentially is you would get a set of results of the modes and the modal frequency. There are some resources available on our website that actually explain this, I believe, in detail. So this is what you would typically get as a result from your modal analysis. So you get your modes. So this is the sort of fundamental mode, the lowest resonant frequency, and then you go higher order, and the frequencies that these modes exist at.
Okay. So we've got 3 more questions. Exactly.
Okay.
Yeah, so another question from Prachi: can DGFEM also be used for models where wavelength max wavelength similar to ratio wavelength maximum geometrical scale is similar to 100? So it's essentially similar to ray acoustics range. I suppose you partially answered this question already.
We have an example of a room problem which is computed using DGFEM, where the wavelength is very small in comparison to the size of the room. So it can be done, but from a computational point of view, it will take a long time to compute. So, probably hours, if not several hours, whereas your ray acoustics equivalent may compute in minutes.
Mm-hmm. Another question from anonymous attendee. I don't know whether we've got time for this, but you decide, Robbie. Can you briefly explain why DGFEM requires low computational cost compared to conventional FEM?
So the reason is that conventional FEM will generate a system matrix or stiffness matrix if you prefer. And the costly part of solving something using the finite element method is actually inverting this large stiffness matrix. Now, DGFEM actually bypasses this. It doesn't rely on generating a large stiffness matrix, and therefore it doesn't need to invert a stiffness matrix. So it removes the costly step from the solution process, and that's why it uses less computational resources. So there's no stiffness matrix that's generated.
Okay, and I think I've got last question from Jamie. If we were to simulate the pressure over a boundary, can we map pressure to be non-uniform over that boundary?
Mm-hmm.
And and then it continues. Wants to simulate a diffuse field pressure of different incident angles across the boundary.
Mm-hmm. So you can use different methods, one of which would be an interpolation function. So if you have pressure data and XY coordinates, you can load that into COMSOL into a function. So if I just quickly jump over to the software. So if I add here a function, I can add an interpolation function here. So I could load in a file where I had X, Y coordinate and pressure, and then I could map that data onto the model using the interpolation function. So you could do that, yeah.
Okay, I think I have all questions asked and answered.
Okay.
If there are no more questions, it's time to finish our webinar. So it will be edited and uploaded on UKAN YouTube channel. Robbie, you also mentioned slides will be shared. Could you
Yes.
email them to me? I can actually attach them to the YouTube video as well.
Mm-hmm. And just to reiterate that if anyone wanted to contact us for a trial, then they can contact my colleague, Oliver, and he can share a trial with anyone that is interested.
Yes, thank you.
Yep,
And
no problem.
I'll stop the recording.